Hi there, and welcome back to the Joy of Calculus. Today, what we're going to be doing is a little FRQ that I got right here. The first question reads, the function f has derivatives of all orders for all real numbers x. Assume f of 0 equals 1, f prime of 0 equals negative 2, f double prime of 0 equals 6, and f triple prime of 0 equals 3. Part A reads, write the third degree Taylor polynomial for f about x is equals 0 and use it to approximate f of 0.5. Well, today, first what we're going to be doing for this problem, we're going to just take the pen right here, just put it to the paper, just a little A right there. Let's go over that a few times. Make sure it looks nice and clean. Then, for the first term in the Taylor polynomial, we just take f of 0, which is 1. Right there, just some smooth little lines. That's alright if you make a few accidents, it's quite alright. Then the next term, you add f prime of 0, which is negative 2 times x minus what it's centered around. Now in this case, it's centered around 0, so you don't have to worry about that. And it's the first degree, so it's just a little 1 up here, and it's all over 1 factorial. Then the next term right here is plus f double prime of 0, which is 6, times x again, but this time to the second power, and all over 2 factorial. And for the last degree, what you're going to do is you're going to do the same thing as before. Just a little 3 right there. Same old thing. Just make sure you really focus on the lines. Right there. And now, what we can do is we can simplify that. So down here, we can do 1 minus 2x plus 6x squared over 2 plus 3x cubed over 6. And we can take that one step further. Make that 1 minus 2x plus 3x squared plus 1/2 x cubed. And for the second part of the problem, what we have to do is approximate f of 0.5. And now that's easy, because we already have the Taylor polynomial set in place. So all we got to do for that is plug it in. And when you do that, you got to be real calm with it. Just a nice clean stroke. Just real relaxed. And so, well, you can see we made a little happy accident right there. We got to make that approximate. Because it's not the exact answer, just an approximation. And if you do this, we get this right here. And then you can simplify this one step further, cross out the 1's, and that right there is 13/16. And there you have it, part A of the FRQ.
Hello, welcome back to the Joys of Calculus. Alright, for part B, the fourth derivative of f satisfies the inequality. Absolute value of the fourth derivative of x is less than or equal to 8 for all x in a closed interval 0 to 0.5. Use a Lagrange error bound on the approximation f of 0.5 found in part A to determine if f of 0.5 could be 0.8. Alright, so first we're just going to draw a heavy little B here. So first off, we have to set up our Maclaurin series. Formula for Maclaurin series is going to be m over n plus 1 total. Made a little mistake there, but there are no mistakes in calculus, just happy little accidents. We're going to multiply that times x minus a n plus 1. So since we're focusing on the third derivative here, in order for our arrow bound, we're going to use n is equal to 3. And since we know that the fourth derivative is less than or equal to 8, we know that our m is going to be 8. And because x is centered around 0 because it's a Maclaurin series, it's going to be x minus 0. So I'll read this out. And there we have our happy little Maclaurin series, our Lagrange error bound. So now what we're going to do is we're going to plug in 0.5 for x. So we just do this little here. And we're going to be using a nice titanium black marker for this one. You're going to see that our equation is going to equal 0.02083 repeating. And so now for the second part of the question, we're going to take a look back at our answer from A. So since we know that's 13/16, which is going to come out to about 0.8125, that is going to be what we're going to be basing our error bound on. So we know that f of 0.5 is less than or equal to that. And all we're going to do is we're going to subtract 0.02083 from this one and add 0.02083 to this one. So just going to do that right now. Made a little happy accent there. And that is going to give us 0.716, which is less than or equal to the approximation of f of 0.5, which is less than or equal to 0.8333. So we look at part B. It asks us to determine if f of 5 could be 0.8. And looking at the error bound, we can determine that because it is between 0.7916 and 0.8333, yes, f of 0.5 could equal 0.8. Alright, welcome back to the Joys of Calculus with this happy little FRQ here. And now we're going to keep going on with part D. So I'm just going to start with my titanium black. Get a happy little D on here. There you go, just like that. Now part D says, write the fourth degree Taylor polynomial for g, where g of x equals f of x squared. Now, before we do this, we need to clean our brush, so we're just going to take it, chop it up like so. Just got to beat the devil out of it. Just like that. Real easy. Alright, good. Now that's clean. We're just going to take it, and we want to recall our Taylor polynomial from part A from earlier. So all we're going to do is take that function and replace the x with an x squared, just like so. So you're going to start with this 1. That stays the same, there's no x there. Alright, put the minus like so. And we're going to take this x, replace it with an x squared. Just like that. There you go. Alright, good. Now, one more term. We just need to add the next term, plus 3. And we'll replace the x squared from earlier with an x to the 4th to square it, just like so. That's as far as you need to go because this is only a 4th degree polynomial.
Hope you have a nice day.
Just like that.
Again, it's the joy of calculus with us three, Sapphire, Scott, and Cameron.
We're going to start off today by taking a look at this logistical differential equation. This models the population growth of a population, and you can tell that because we have a decimal here, a p-value outside of parentheses also containing a p-value. Now, let's take this little accident that the College Board thought up of, and we'll apply it. And we'll find the general solution to this differential equation. So let's just go ahead and take a look at the problem. First, we can factor out a 30 because in order to simplify the differential equation, you have to get this number to a 1. So let's go ahead and do that. So we'll have dp dt equals, let's factor out that 30 there, put as 0.03 times 30 times p again, which stays there, times 1 minus p over 30. Now, we can simplify this even further by taking this down. That's an arrow, a little accident that I made there. And we can say this equals 3 over 100 times 30. We can cancel out the zeros and add in the rest of our information. So, if you know 3 times 3 equals 9, you end up with dp dt equals 9 over 10 times p to the 1 minus p over 30. Now that we've successfully simplified our differential equation, we can now apply it to find the general solution to this equation. But let's take a second and remember our equation for solving the differential equation. We know that p sub t equals k times a e to the kt over 1 plus a e to the kt. Now, in this equation, k here describes the maximum carrying capacity of the population, whereas this k describes the rate of growth, which we can get all of this from this dp dt equation. So let's go ahead and take this information and we'll put it into this one. So we're going to go ahead and write p of t equals k, which is our carrying capacity, which is this 30 right here, 30 times a e to the k times time, k is our rate, 9 over 10, which is 0.9 times t over 1 plus a e to the 0.9 t. And there you go, there's our answer.
Part B asks us, find the particular solution of the differential equation given that 5,000 people have the disease when first noticed. That is, when t equals 0, p equals 5. So let's take our nice pen here. And, before we do that, let me just get my stuff ready. Alright. So we have this, right? So now, we'll plug in 5 for p and 0 for t. 5 equals 30 at 30 a e to the 0.9 times 0 over 1 plus a e to the 0.9 times 0. Now, we know that any number to the power of 0 is 1. So this simplifies too. 5 equals 30a over 1 plus a. Now, all we're going to do here is solve for a. Cross multiply. 1 plus a times 5, you get 5 plus 5a equals 30a. Now, if you guys took Algebra 1, 2, you know how to do this. Just combine the like terms, subtract the a's over, you get 5
equals 25a. So, a equals 1 over 5. Now, let's just plug this into our original equation here. We get P of t equals 30 times 1/5 e to the 0.9t over 1 plus 1/5 e to the 0.9t. We can simplify all this, just add our multiply our 1/5 and change them to decimals and all that good stuff. We get this final answer of P of t equals 6 e to the 0.9t over 1 plus 0.2 e to the 0.9t. And that's your particular solution. So here, we solved this differential equation, this logistic equation, for the general and particular solution.
Yes.
Thank you for watching, and we'll like to see you next time on The Joy of Calculus. Like, subscribe, share.